Hey everyone, thank you for joining us today for this webinar. Jason Allen here, the concrete pipe guy. I'm the technical resource engineer for Oldcastle Infrastructure, and I will have the pleasure of presenting today's webinar, the topic of which is inspection and evaluation of reinforced concrete pipe after installation. So before we begin, I want to tell you a little bit about myself. So I currently live in Utah, and I am a proud graduate of the University of Utah with bachelor's and master's degrees in civil engineering. Now, I've been in the engineering industry for over 20 years, and I started when I was 18 years old as a land surveyor. Did that for a couple of years, and then I moved on to drafting and design, and mostly in land development projects. I then worked in the public sector of engineering as a county engineer and public works director. And after that, I got back into consulting and did some large roadway and drainage projects for the transportation Department of Transportation and large municipalities, and had a lot of fun doing that. But now I do more marketing and technical resource engineering for Oldcastle Infrastructure. So some of you may not be familiar with Oldcastle, so I'm going to quickly share some of the solutions that Oldcastle Infrastructure can provide. So as I mentioned before, I currently live in Utah, spend a majority of my time providing technical resources to design engineers, contractors, and inspectors in the Mountain West area. Now, most people know us by our precast products, mainly reinforced concrete pipe and precast box culverts, and we also provide precast manholes and catch basins. Now, this has been kind of our main focus for many years, but recently we have added some really cool new product lines that can help meet your needs. So Oldcastle recently acquired Torrent Resources. This is a company out of California, and it's the industry leader in drywall manufacturing and installation. We've also expanded our stormwater solutions to include storm capture, a total stormwater management system that uses precast sections for underground detention storage. Now, this system uses the strength of reinforced concrete to provide more volume for storage, which drastically reduces the footprint compared to other underground detention systems you may have seen on the market. Now, we have also included some really cool stormwater treatment system options like sediment traps and hydrodynamic separators that could fit your specific low impact development needs and your stormwater treatment requirements. Our newest addition in the Utah market is gasketed box culvert. Now, instead of your typical soil tight or silt tight mastic joints, we now have the ability to manufacture gasketed box culverts to provide a watertight or leak resistant joint without any additional joint treatment, which saves time and money on installation. Very cool new product that I suggest you look at. Okay, so in a previous webinar, we discussed the basics of post-installation inspection, or PII. Right, today, we're going to dive a little bit deeper into that with inspection and evaluation of reinforced concrete pipe after installation. So let's jump right in. All right, concrete cracks. Fact. Thanks, Dwight. One of the questions I get asked most by inspectors and municipal engineers is what cracks are acceptable? They'd say, Jason, we know that concrete cracks, we understand that, but how big of a crack is okay? What can we tell this contractor is okay and what needs to be fixed? So about 7 years ago, I was invited to sit on a committee that wrote a national ASTM specification called C1840 that covered the guidelines for the inspection and evaluation of RCP after it was already installed. Okay. This specification was adopted in late 2017, and the specification has become an absolute game changer in the reinforced concrete pipe industry. So after decades of relying on guidelines and recommendations from our industry professionals like myself, we finally had a codified specification with objective and measurable criteria for the acceptance or rejection of reinforced concrete pipe. So the sections of ASTM C1840 are as follows. Section 1 goes over the scope of the spec. Section 2 goes over all the reference documents, whether ASTM specs or AASHTO, different guidelines there. Section 3 is all about the terminology and the definitions. Section 4 talks about significance and use for the spec. Section 5 talks about pipe inspection equipment and the procedures. Section 6, equipment and operator accuracy verification. Section 7 discusses the requirements for inspection reports. And Section 8, which is kind of the one that most people focus on here, and kind of the whole crux of this spec, is the installed pipeline evaluation and acceptance criteria. Now, when we talk about inspection of pipe that has already been installed, ASTM C1840 recognizes there's really only two ways to accomplish this. The first, which is shown in the figure on the left there, is person entry inspection. Now, this is common in large diameter pipe that is large enough that a person can walk through it. Now, the second and the most commonly used method in our market, at least, is remote inspection camera or remote controlled CCTV inspection. Okay, so this is used in small diameter pipes because about 99% of the pipe that I get to inspect is too small to walk through. This is what I see more than anything. So I get asked a lot, so what should we be looking for in these inspections? When hiring a professional to do your video inspections of the pipe, I would suggest that you find someone that is NASSCO PACP certified. All right, so what is the NASSCO PACP certification? Well, I am so glad that you asked. I thought you'd never ask that question. I've been dying to tell you, so let's get into it here. So NASSCO is the National Association of Sewer Service Companies. NASSCO's mission is to set industry standards for the assessment, maintenance, and rehabilitation of underground infrastructure and to assure the continued acceptance and growth of trenchless technologies. NASSCO's vision is to increase the awareness of aging underground infrastructure and to provide viable solutions through education, technical resources, and industry advocacy. Now, NASSCO offers three separate certification programs. There's the PACP, the LACP, and the MACP. So PACP stands for Pipeline Assessment Certification Program, and LACP stands for Lateral Assessment Certification Program, and MACP, yep, you guessed it, Manhole Assessment Certification Program. So these are the trusted sources for proper and consistent assessment condition coding of pipelines. So this is for the assessment of pipelines, laterals, and manholes. Now, the goal of these programs is to help pipeline system owners create comprehensive databases to properly identify, plan, prioritize, manage, and renovate their assets based on condition evaluation. It is important to keep in mind that these programs are meant only to assess and code issues within utility systems. These certifications and programs are not intended to provide recommendations for like maintenance or remediation of any issues that they identify. They're only there for assessment. Okay. So in order to better understand the inspection videos that I was watching in my job, about 5 years ago, I decided to sign up for a class and get my PACP certification. Interesting side note, it was in Las Vegas in August. So, yeah, it was pretty miserable. It was like 120 degrees, but that's neither here nor there. Anyways, this picture that I've got here on the screen now, this is a picture of the manual that I was given in the class. If you are wondering, yeah, that's like a 3-inch binder. So there is like a lot of information in there. Okay. A lot of information, very valuable information, but this right here, this picture up on the screen here, this right here is the key to all the information in that binder. All right. This is the color-coded chart for all of the coding that NASSCO professionals do when they're evaluating and inspecting a pipeline. So this picture here, this one card that they gave us, this addresses any of the issues we might find within a pipeline and lays out the nomenclature for all the correct coding. All right. So if this looks confusing, don't worry. I'm going to get more detailed in a little bit, and I'm going to go through each of these and kind of tell you what they are and show you how it works. But so this sheet here is for section 4 of the manual, and this addresses structural defect coding like cracking or breaks in rigid pipe, deformation or collapsing in flexible pipe. It also looks at like joints and surface damage, both of which can apply to rigid or flexible pipe systems. Section 5 deals with codes for operation and maintenance issues, including deposits of like sand and other debris. There's a whole section just for identifying roots within a pipeline. There's the section on infiltration, obstacles and obstructions, and my personal favorite, vermin. Interestingly enough, I should point out here that vermin, if you look, there's that blue box there with the V, vermin. There's really only 3 options for coding vermin, which I thought was kind of interesting: rat, cockroach, or other. I'm not 100% sure why this intrigues me so much and why I'm so fascinated by the fact that the only vermin you can code are rat, cockroach, or other. But I don't know. It just is interesting to me. I don't know. Whatever. Okay, so let's go back to section 4, like we talked about. Remember, that's about structural defects. So let's look at the 4 most common issues found in an inspection of RCP. All right, so the first blue box there is for a crack. Now, the C in the top left-hand corner shows what the initial code is for a crack. So if you find a crack, we know it's going to be a C. The numbers in the top right-hand corner are the page number for easy reference in the manual if you have any questions or need examples of different types of cracks. So each of those pages in that manual, there's just page after page after page of examples, right? And so it's really helpful to say, okay, what does this one look like? And you can compare and contrast and find which one looks like what you're seeing so that you can ensure that you're coding it correctly. Now, as you've done this for a lot of times, and as you go through and identify these, they start becoming second nature on how you code them and how you identify them. So it gets easier over time, but at the beginning, you're referring back to that manual a lot. So it's good that they provide a lot of visuals and detailed pictures and images, and it's all in full color, so it helps you really see what you're looking at there. So anyways, the once we've identified it as a crack, okay, there's 5 additional options for a crack to get a little bit more specific in the coding. All right, so for a crack, you've got like CL would be for a longitudinal crack, CC for a circumferential crack, CM for multiple cracks, CS for a spiral crack, and CH for a hinge crack. Now, similarly, fractures have the same 5 options for additional coding. And then you've got also like a broken pipe has the option of like BSV, which is broken, soil visible, or BVV, which is broken, void visible. And then a hole has the same options as a broken piece of pipe. So before we go any further, I think it would be good to go over the difference between a crack and a fracture as defined by NASSCO, because some people may not really know, and they may be calling cracks fractures and fractures cracks. So we want to make sure that we're getting those identified correctly. So a crack is a break line visible on the surface, but is not visibly open. So there's no gap visible between the edges of a crack. Now, a fracture, on the other hand, is a break line that has become visibly open and a gap can be seen. So the pipe wall in this case is still in place and doesn't move, but there is a gap, and the side of the cracks can be seen in that case. All right. So because cracks and fractures are the most common and have the most secondary classifications, we should make sure that we understand exactly what those codes mean. So the L for fractures and frac is longitudinal. I should say cracks and fractures. Sorry, longitudinal is L. This is lengthwise, a crack or fracture that is lengthwise and is parallel to the center line of the pipe. Now, the C is for circumferential. This is a circular pattern, and it's parallel to the joints, so it goes around the inside of the pipe in a circular pattern. M would be for multiple. Now, this is a combination of intersecting, longitudinal, and circular cracks. So if there's multiple cracks all throughout that pipe section, that's what they would code it as multiple. Now, spiral is one that changes position as they travel along the pipe. So if you have one that's going from longitudinal to circumferential, that would be a spiral crack. Okay. A hinge crack is more than one longitudinal crack at the same footage at the 12, 3, 6, or 9 o'clock positions. So that would be, you've got a crack at top and bottom, or you've got a crack at the spring lines, or you've got a crack at all 4. Okay, that would be your hinge crack. So going back to this, now that we know what all of those are for the cracks and fractures, you could see the CL, CC, CM, CS, CH, FL, FC, FM, FS, FH. All right. So for example, if you were to see, if you're reading through an inspection report and you see a CC, right, you would look at this little cheat sheet here and you'd say, oh, CC means it's a circumferential crack, right? And if you were reading through the report and you saw an FL for example, that wouldn't stand for Florida. That would be a longitudinal fracture, and so on and so forth. So let's take a look at a couple of examples of each of these, and so we could see what we're identifying and identify them correctly. So this one, obviously, CL, crack longitudinal. You could see the crack along the spring line there of the inside of the pipe. It runs parallel to the center line of the pipe. It's running along the barrel. That is a longitudinal crack. All right. Now, this one here, if you look at the top of that picture, this is kind of an interesting one. This is a brick pipe. This is right out of the NASSCO manual here for PACP. At the top of that pipe, you can see that it's more than a crack. It's an actual fracture. You can see the gap there. So that is a longitudinal fracture, or an FL, fracture longitudinal. So that's kind of a cool picture there. This is one that would be a circumferential crack. So this would be a CC, crack circumferential, right? It goes around, it's parallel to the joint. It's going around in a circular pattern, pretty easy there. This one is also out of the book in section 4 there. This is a fracture spiral. You could see that it's a gap, so we know it's a fracture. It's not just a crack. It's not just on the surface. We can actually see the gap, so we know it's a fracture. And notice on the right-hand side of that picture, it's coming in as a longitudinal, and then it immediately dives down into a circumferential crack. So that would be coded as a fracture spiral. All right. And then this one would be not only crack multiple, but hinge crack. So this would be a CH, crack hinge, and then you would also put how many quadrants it's in. So in this case, you could see it at the spring lines, and you could see it at the top. So we've got one at 12 o'clock, one at 3 o'clock, and one at 9 o'clock. Now, we can probably assume that there's one at the 6 o'clock position. However, when we're coding these and when we're going through and inspecting, it's not our job to assume. Right. So we're not going to say that it's in 4 quadrants. So we're not going to say CH4, because even though there's water and there's debris and there's silt and things, deposits that are along the bottom. So we can't fully tell that there's a crack. If you cannot see the crack in the bottom of the pipe, don't call it out. Right. It might be there, but it's not for us to make those assumptions. So we would just put CH3 because that's all we can see. All right. Okay. So that's for cracks and fractures. Now we're looking at another issue. The other most common issue would be joints, right? So you've got some coding for joints here. So you've got 4 different options for joints. You've got offset, defect, separation, and angular. So with offset, you've got offset small, JOS, joint offset small. You've got JOM, joint offset medium, JOL, joint offset large. So the first picture there, figure 13, shows a joint offset, and they've got that coded as JOM, or joint offset medium. So that would be where your joint is actually offset a little bit so that it has vertically, it is coming into the pipe a little bit there. Okay, so that's your offset. The next one would be a defect. So for instance, if there's minor spalling at the joint or something like you could see in figure 16 on the right there, that would be defect. So that one could be JOSD, joint offset small defect, because there's some cracking or some breakage there at the joint there, just right as it comes in there. The next one here, figure 14, you can see this would be joint separation. We sometimes in the industry refer to those as joint gaps, but NASSCO calls them joint separation. So this one would be either joint separation small, medium, or large. And then the fourth one would be your angular. Now, sometimes as pipe is installed, it comes in at an angle, right? So it might have no joint gap on one side, and then directly across from the pipe, it might have a really big joint gap. So you can make that assumption there, and you could say, okay, because it's that way, it's coming in at an angle, whether it's vertically at an angle or horizontally angled, but we could code that as like JAS for an angular small, JAL for angular large, or JAM for angular medium in there. So that's that other figure there on the bottom right-hand side of your screen that shows your angular joint. Okay, so we've also got codes for infiltration. This is another thing that we see quite often, different infiltration things. There's actually 5 of them, 5 different levels of infiltration according to NASSCO. All right, so those are stain, weeper, dripper, runner, and gusher. And within each of those, you can identify where the location is of each of those. So for instance, if it's just a stain, right? There's no water coming in, but it's stained because maybe water has come in the past and now it's sealed itself back off. And so the water isn't coming, or maybe it was flowing in there because of high groundwater and now the groundwater is low, so it's not coming in anymore. But as we go through, we identify and we see that there's a stain. So like figure 17 shows rust colored staining on the pipe there. Right. So we could say, is that at the joint, ISJ? Is it on the barrel of the pipe, ISB? Is it at a connection between two pipes? Now, that's not very common in RCP because our connection would be at a joint or at a junction box. But, you know, if you've got a Y or something in a metal pipe, or in a, you know, like a plastic sewer pipe or something, as it comes into a Y, that could be a connection. Or is it at the lateral? Again, we don't really see a whole lot of laterals in concrete pipe as often, but every now and then we'll see that. So you've got a stain. The next one would be a weeper. So a weeper would be, a little tiny bit of water coming into the pipe. So if there's any water at all coming in and it's just really minor, we're not really seeing the water come in, but we could see the staining and we could see that it's wet. So we know the water is coming in, but we're not really seeing it flow in. That would be a weeper. Okay. The next one would be a dripper. Okay. So this is one where we're actually seeing water come into the pipe, right? And again, you would identify where is that dripper. So ID is infiltration dripper, and IDB would be within the barrel of the pipe. But if you see water actually coming in, flowing into the pipe, albeit maybe at a low rate coming in, but if you see it flowing in and flowing along the surface of the pipe wall, that would be a dripper. Okay. Now, the last two would be a runner or a gusher. Now, a runner means we're seeing water come in pretty quick. That's typically at the top of a pipe where it's running in and it's dropping in at a high volume there, or even coming in from the side of the pipe and it's just coming in really fast. That would be a runner. Now, a gusher is one where we actually have water under pressure. Maybe it's high groundwater and there's a hole in the pipe or a crack in the pipe, and you're seeing water actually spray into the pipe. That would be considered what NASSCO would consider a gusher. All right. So these CCTV inspections are extremely helpful in identifying issues within our pipelines. And I need to point out that not all inspections are created equal, and there are some things that we should be watching out for. So, for example, we need to make sure that the camera is centered within the pipe. If it's not in the center of the pipe, and let's say it's too low, as you go around the circumference of the pipe, as you go around the joint, things at the bottom may look really big. Any issues or defects at the bottom may look much bigger than they really are, and issues and defects at the top of the pipe may not look as severe because of the way these cameras work and these fisheye lenses and the distortion there. If it's not perfectly centered, you're going to have issues as you go around the pipe. We also want to make sure that the camera is moving slow enough to see issues. I've seen a handful of videos that just these cameras just fly right through, and you just can't really identify any issues because it's going too fast. Now, NASSCO recommends that you go a maximum speed of 30 feet per minute. All right. Another thing you want to make sure is that your operator is stopping to document any cracks or damage or any other issues within the pipe. If there's any obstructions or, any roots or anything coming into the pipe, the operator really needs to stop and document those. Okay. Another thing that I always recommend that I like to see is I want to see the full circumference at every single joint. So as they go 8 feet in a concrete pipe, stop. The camera pans over, it looks at the joint, it goes all the way around the full 360 degrees around the joint to make sure that there's no issues there, that there's no, exposed gaskets or issues or joint gaps that are too big or joint separation that are too much, any offsets. Those are the things I'm looking for. So we want to make sure that our operator is going around the full circumference at each of the joints. Another thing to watch out for is to beware of any zooming in and out, right? When we zoom in, on some of these pipes, some of the issues can look a lot worse than they really are. And I'll go over this a little bit more when we get into the inspection report part, but zooming in can be a real problem. You've got to watch these videos in context to ensure that, they haven't zoomed way in so that the crack looks bigger than it is, or the joint gap looks bigger than it really is, right? Another thing that I notice a lot is the coating, how they're coating them. Sometimes they'll call something a crack when it really should be a fracture. Sometimes the severity of them and just the nomenclature that they're using. I always ask, I want to make sure that they're NASCO PACP certified. I've seen some cracks sometimes where they'll say like big crack or large crack. It's like, well, that's not the correct coding. Like, why are you, what's one person considers large may not be large to another person. And so those things can really raise red flags in the inspection reports. And as city engineers who maybe don't look at these videos as often as other people in the industry, as they're looking at that and reading through it, they're like, oh my gosh, it's a large joint gap or a large crack, or it's really big cracking, or whatever they're calling it. That could be problematic as we go through it and look at it. Another thing to really be concerned about is images versus video. Sometimes someone will just take an image, a screenshot of the video, and send it to me and say, hey, is this okay? Is this acceptable? Is there anything wrong with this? And I really can't get the full idea of what's going on unless I watch it in context with the video. So I typically won't review any images and just write a letter based on an image, because I need to see it in its entirety. I need to see what's going on, what's causing this. I need to look at it and see if I can identify any, what the underlying cause of this issue really is. And then the last thing that I always watch for is I want to see the inspection report. I want to make sure that they're not just videoing, but they're providing the client with an inspection report that really goes into detail of what we're seeing, so that it helps me kind of summarize what I'm looking for and helps me to go and know exactly what the operator saw as the issues. Now, that doesn't mean that sometimes when I'm going through a video and I see something, I might see it a little bit differently as them, or I might actually see issues that they didn't see, or maybe they're seeing something different. I've seen times where they'll call out like a large crack or a defect, where really all it was just a scraping or a discoloration from like a forklift lifting the pipe, and they're calling that a big crack, and it's really just a little surface scratch. And so there's times when I'll find things that are maybe not coded correctly or not correct as they're moving quickly through there. But that's why I want to see the report. I want to see what they're seeing and what they're calling it, and I want to see all of their field notes and look at that. So this is an example of an inspection report that I saw on a project one time. Really good inspection report. This company did a really good job. You could see I blocked out all of the pertinent information, so you can't see who the client was or where it was at. But as you can see, as it goes through it from start to finish, it tells you what point they're starting at, what the start point is, what the end point is. And it goes through and identifies each of the issues that they found at each of these locations along the pipe run. And as you go to the next page, as you look through there, it actually shows you any of the observations that they saw with pictures. And that's what I always like to see, is the screenshot, so that I can see the picture that they're seeing. So we're going to actually take these two issues here. We're going to zoom in a little bit here. And this is what we're looking at. So notice the first number there, 0.0. That's it. That's the start point. So that's how far along they are on the pipe. So this is right at the beginning where it's connected to the catch basin there. And then the coding is CC. And that would be a circumferential crack, we know, right? The other one at the very end there, the only other pertinent information on this is the very end where it says 5 to 8. That's just the location. It just says where the location of the crack is in relation to that. So that's one thing to keep in mind. But then when you go to the next one, you've got 22.5. So that means that at a distance of 22.5 from where they started, they found an issue with a joint, right? So JSM, we know that J is joint. We know that S is separation, and M would be medium. So joint, separation, medium. Now, that's how they identified it. And when I look at that picture, I think, well, again, I can't really tell from a picture. I want to see the video so that I can see, are they zoomed in? What if they're zoomed way in? I mean, to me, honestly, that circumferential crack up there, that looks like they're zoomed way, way in, just based on the size of the aggregate as it's showing up in the picture. It looks like they've actually zoomed in. So I want to see this. Did they zoom in to get this really good picture so it looks bigger or worse than it really is? I don't know. So I want to see the video. And what I'm looking for when I look at the videos here, I'm going to give you an example here. So this is a picture of a video that I took. And the reason I like this is because it's got a little crack there. And if I zoomed way in, that crack would look really big. But when I zoom out, I can use some context clues, and I can see some things that I'm looking for. So for example, on the right-hand side of the screen, you've got a stencil there that says Oldcastle 18-inch. So that stencil is 1 inch. So as I go through and I'm looking at that and I'm identifying, okay, that's 1 inch. I can compare that 1 inch to how big that crack is, and I can see that that crack in that on that screen there, it is a longitudinal crack, but it's hairline. It's very small, right? You're not going to have any issues there. That's going to be an acceptable crack because it's less than a hundredth of an inch. It's very small. But when I look at the joint gap, or that joint separation there, I can identify whether it's within our manufacturer's recommendations or not, just by comparing it to the size of that stencil, that 1 inch stencil that we spray painted on the inside of our pipe. I can look and say, okay, if a joint gap, an acceptable joint gap is, let's say it's 1 inch, right? Okay, well, that's the height of that stencil. Oh, yeah, we're definitely well within 1 inch there. What if it's a half an inch? Well, I can kind of scale it off and say, oh, yeah, we're within a half an inch. We're good to go there. So these kinds of things really help me identify whether or not these issues that are showing up as pictures in the inspection report, if they're going to be an issue in the long term, and if there's something that's going to be acceptable according to the specs or require some remediation. Okay, so again, going back to there, that's, now that we've seen it in context, I can say, all right, well, I need to go to this pipe run, and I need to go to the video, and I need to look at that joint gap, so I can know if it really is as bad as they say it is. Okay, so there's a handful of similarities and a few differences in the nomenclature and the naming between NASSCO and ASTM C1840. So I'll go through a few of them for you here. Longitudinal cracks, so a CL crack longitudinal, that's the same in both. They call NASSCO and ASTM both call it a longitudinal crack. Same as circumferential cracks, those are the same, right? A hinged cracks, similar, right? They call them hinge cracks. They call them in the different quadrants. Typically, you're going to see those at 3, 6, 9, and 12, but that's it. This one is a little bit different. This one, they call it a multi-directional crack. So if you remember, the NASSCO called these a spiral crack. So that's one that starts in one direction and then shoots off in another. So ASTM C1840 calls it a multi-directional crack, while NASSCO calls it a spiral crack. So as far as infiltration is concerned, I mentioned there were 5 different infiltration things with NASSCO. You had the stain, you had the weeper, a dripper, a runner, and a gusher. With ASTM C1840, they've broken it down into 3 different levels of infiltration. So the first level, or level 1 infiltration, is your stain and your weeper. So if you can't really see the water flowing and the water coming in, but we know that there's water coming in because it's wet and you could see the stains, then we would call that a level 1 infiltration. All right. With level 2 infiltration, this is where you can see in the video that water is clearly flowing in. You can actually see the water coming in. And so that would be similar to your dripper in your NASSCO certification. So a dripper is the same as your level 2 infiltration in ASTM C1840. All right. Then we've got our level 3. So this is water being, spraying in and running in. So these would be your level 3 infiltration would be the same as your runner or your gusher. So if water's forcefully spraying in and pushing through that hole or through the crack or through the joint, that would be your level 3 infiltration. So this is one thing that I really love about ASTM C1840. Here are a few other things that it talks about in there that kind of shows you some pictures, but most of the specifications in ASTM, kind of interestingly enough, they're all in black and white. They've got maybe figures and diagrams drawn, but ASTM C1840 is in full color. So it has all of these different pictures in full color that you can use to help you kind of identify things and issues. So it's kind of a cool and a unique spec because it's really one of the only ones that I've read through and seen that actually has full color photos in it. So kind of awesome. But, they have the similarities with the offsets, joint offsets, as you can see in figure 13, figure 14, same thing, joint separation. So ASTM has the same nomenclature as NASSCO. Figure 15 shows you some slabbing, there's spalling at the joint, staining, different things. So it's really cool with all the different pictures and figures and images that it shows in this spec. It makes it a really unique and interesting spec. When we were writing this spec, we kind of went back and forth on, do we just describe everything, or how do we do this without using pictures? And it ultimately came back that there's really no way to have a spec like this without having pictures in it to show you what we're talking about. And so we could try to use words to describe this as much as we can, but at the end of the day, we know that a picture's worth 1,000 words. And so this is a much easier way to write this. But I can't even imagine how long this spec would have to be if we went through and really went in detail of what each of these things were in just written form. So these pictures are super invaluable, these full color photos. So kind of a cool spec. Anyway. All right, so notice on this circumferential crack that there's a white effervescent coloring around the crack. Right now, we discussed this phenomenon in detail in a previous webinar, but ASTM C1840 discusses it as well, so I think it's worth reviewing here. So we call this autogenous healing in the cement and concrete industry, is what we call it, autogenous healing. ASTM C1840 calls it calcium carbonate filled pipe. So a little bit different wording and naming convention than what I'm used to, but that's what we decided to call it in ASTM C1840. Instead of saying autogenous healing, which not everybody knows what it is, we decided to go a little bit more specific on what it is, and that is calcium carbonate filled pipe or calcium carbonate filled crack. All right. Autogenous healing or calcium carbonate filled pipe is the ability of concrete to heal itself in the presence of moisture. And what it does is it actually seals the cracks and creates this white effervescent material. So let's talk about the science behind autogenous healing. So within the cement in our mix, there's always some free calcium oxide. Okay. Now, as the tricalcium silicate in cement is hydrated by the moisture within the pipe, the calcium hydroxide is liberated. Now, we also know that there's an abundance of carbon dioxide all around the pipe, whether it's in the air or in the soil or the water. And what happens is that this CO2 is absorbed by the concrete itself. And the CO2 actually carbonates the calcium oxide and calcium hydroxide. And this process creates calcium carbonate crystals, or basically limestone, and then it just seals in that crack. So that's the science behind autogenous healing, and that's how it's done. Kind of a cool little process there. All right, so now we've discussed the differences, the definitions and the evaluation procedures within ASTM C1840. So let's get down to the nitty gritty and what everybody really came for. Section 8. This is why we're here. This is what people really want to know. This is all about the evaluation and acceptance criteria in installed pipelines. So in other words, this is the answer to that original question that I proposed. What cracks are acceptable? All right, so rather than just throwing the spec up on the screen and just reading through it, I'm just going to give you a quick summary of what is acceptable according to ASTM C1840. And I'm really going to focus on the two most common issues here. That would be cracks and joints. All right, so first, we're going to talk about cracks not requiring any additional evaluation or remediation. So according to ASTM C1840, these are the cracks that are acceptable and don't require any additional evaluation or any remediation. All right. So first of all, we have any longitudinal cracks that are less than 1/100 of an inch wide. So these are your hairline cracks. These are acceptable not only per ASTM C1840, but we know that these are also acceptable per ASTM C76, our manufacturing specification. Next up, we've got longitudinal cracks that are less than or equal to 5/100 of an inch wide. If you remember from previous presentations, we've talked about how much 5/100 of an inch is. That is the width of a dime. So if it's less than or equal to the width of a dime, and it's up to the entire pipe segment in length, so it can go from one end of the pipe to the next end of the pipe along the barrel of the pipe, and it's less than or equal to 5/100 of an inch, or the width of a dime, and it's in a non-corrosive environment. So according to ASTO, I believe section 27 of ASTO says that a non-corrosive environment is one that has a pH between 5.5 and 10. So as long as the pH of the soil and everything around it and the water, the material in the pipe, as long as that pH of that material is between 5.5 and 10, then any longitudinal cracks less than or equal to 5/100 of an inch wide are acceptable. Additionally, circumferential cracks less than or equal to 1/10 of an inch in width, including the full circumference of the pipe, so all the way around the pipe, those are also acceptable. They don't require any evaluation or remediation. And the reason is, some people will look at that and go, wow, that 1/10 of an inch, why is almost double a circumferential crack acceptable versus a longitudinal? Well, the reason is that a circumferential crack is not a structural crack. Right? We really don't have, our structural steel doesn't run in the direction of the circumferential crack. And so we can have a circumferential crack. It's no different than having an extra joint. That's how it was explained to me years ago by an engineer who knows far more than I do about the subject. He said, well, Jason, you basically, don't you have a circumferential crack every 8 feet? The difference is that with at those joints, we have, some sealant or some type of gasket to keep it sealed. But he's not wrong. I mean, we have, in some of those cases, we can have up to a 1/2 inch or an inch of acceptable joint separation there. And so, it's really no different than having just a circumferential crack every 8 feet. And so that's why 1/10 of an inch is acceptable in that, because it's not structural in nature. All right. And lastly, multi-directional cracks. So those spiral cracks, if they're filled with calcium carbonate, up to 1/10 of an inch are acceptable cracks. Okay, so if they filled up and they've gone through the autogenous healing process and they're filled with calcium carbonate, those are acceptable. So any of these are acceptable. So sometimes we'll have an engineer look at it and say, well, I don't want this crack in the pipe. It shows a little crack. And we look at it and it's hairline crack, or it's, much less than the width of a dime. And we tell them, hey, according to this specification, it's acceptable. And this is the standard industry practice. This is written by industry professionals and by a lot of engineers that we put a lot of time and effort into studying this and researching it and using, empirical data and different things to show that this is acceptable. So this is a great reference for engineers that are looking for guidance on what to accept in their cities or on different projects. All right, so now we're going to take it one step further. So those were the cracks that were acceptable. So now let's look at any cracks that require engineering evaluation. So this doesn't necessarily mean that they couldn't be accepted. If an engineer evaluates each of these situations and finds out that, it's okay, I write letters all the time based on some of these that I've gone through and done an additional evaluation. And luckily, I don't see a lot of these really bad installations and major issues that often. So we have a lot of great contractors that do really good work in installing these. But if these are some situations, according to ASTM C1840, that would require an engineer to evaluate it and determine if it requires any remediation. Now, I want to point out as well that ASTM C1840 is a specification that identifies the acceptance criteria and what needs to be evaluated and remediated. It does not give any means and methods on how to remediate or how to repair these issues. And the reason is because in different parts of the country, remember, this is not only a national, but an international spec used in a lot of different countries and a lot of different regions. So what we may be doing in Utah and Idaho may not be what they're doing in New York and New Jersey, right? And so some of the methods that we use that work really well here, they may not even be doing those in, say, Texas or in Iowa. So they don't want to dictate the means and the methods, but they will identify which situations an engineer needs to evaluate, and then that engineer can provide recommendations or remediation ideas, or he can also leave that up to the contractor to figure out how to fix it. He can just say, these are the issues that I have identified that need to be fixed. And so I do that quite often, right? So an engineer can look at that and say, yes, these have issues, or no, they don't. So these are the cracks, according to ASTM C1840, that would require additional engineer evaluation. Okay. Number one, longitudinal hinge cracks between 1/100th of an inch and 5/100th of an inch that are in more than 2 quadrants. Longitudinal cracks less than or equal to 5/100th of an inch wide with more than 1/10 of an inch of vertical offset. So if something's going on there where you've got a longitudinal crack and a vertical offset, then that would need to be evaluated by an engineer. Any longitudinal cracks allowing entry of backfill material into the pipe are not acceptable and need to be evaluated by an engineer. longitudinal cracks between 5/100ths of an inch and 1/10 of an inch wide, and up to the entire pipe segment in length in a corrosive environment. So remember, non-corrosive meant pH of 5.5 to 10. So this would be if the pH level of either the soil around it or the material in the pipe, if any of that is outside of that pH level and it's in a corrosive environment, then that would need to be identified by an engineer. Okay, there's a couple more here, so I'm going to keep going here. So these are more situations that require an engineer's evaluation. Longitudinal hinge cracks greater than 5/100ths of an inch wide in more than one quadrant. So we know that if it's less than 5/100ths of an inch in more than two quadrants, it needs to be evaluated by an engineer because there's obviously something structural going on there. If it's longitudinal hinge cracks greater than 5/100ths of an inch wide in more than one quadrant, again, probably have some structural issues going on. Engineer needs to look at that. Longitudinal cracks greater than 5/100ths of an inch wide with any vertical offset. So remember on the previous slide, we said less than 5/100ths of an inch wide with up to 1/10 of an inch vertical offset. This is longitudinal cracks that are larger than 5/100ths of an inch, so more than a dime width, with any vertical offset need to be evaluated by an engineer. Okay. Any longitudinal cracks greater than 1/10 of an inch wide need to be evaluated by an engineer. Any circumferential crack greater than 1/10 of an inch wide in a corrosive environment also needs to be evaluated. And a circumferential crack with an offset that impedes flow through the pipe, that should also be evaluated by an engineer. All right, so now let's look at joints. Now, there are two different types of joints that are addressed in ASTM C1840, and the first is soil and silt-tight joints. So these are just joints that are meant to keep soil out of your pipe, all right? Not necessarily watertight or leak-resistant. Okay, we'll get to those in a second. So for those that are acceptable and do not require any additional evaluation or remediation, they have to meet the following. The joint separation or the gap is less than the manufacturer's recommendation, and it has to meet the following. Okay, if there's a crack width in there, the crack width has to be less than 1/10 of an inch, less than or equal to 1/10 of an inch, or have an offset of less than 3/4 of an inch. Okay, it also has to allow entry of backfill particles less than the number 200 sieve. So it can allow, because remember, it's soil and silt tight joint, so it can let a little bit of particles in there, but they cannot be any greater than the number 200 sieve. All right. If it has any chips or spalls, those are acceptable as long as there's no steel exposed. And if there's either a stain, a level 1 or level 2 infiltration, that is acceptable. That's fine. Now, lastly, if there is an exposed gasket or sill, that is fine, because remember, it's a soil or silt tight joint. Any exposed gasket or sill is okay as long as all of the other things that we just talked about are met. Okay. Now, again, joints not requiring evaluation or remediation. Now let's look at leak-resistant or watertight joints. All right, so again, the gap must be less than the manufacturer recommendation, and they have to meet the following criteria as well. A crack width less than 5/100ths of an inch, a vertical or horizontal offset of the joint less than 3/4 of an inch or 0.75 inches. Okay, any chips or spalls cannot have any exposed gaskets, seals, or steel. If it meets all of those criteria, then that is acceptable, and it does not require any evaluation or remediation. Okay. Now let's look at joints that require an engineer's evaluation. Again, I want to point out that that doesn't necessarily mean that remediation would be required. That's up to the engineer to decide the means and methods and whether any remediation would be required. So leave that up to the engineer to decide. So for soil and silt tight joints, number one, if the gap is greater than the manufacturer recommendation, it needs to be evaluated by an engineer. If there's cracks in the joint sealing surface, so like in the bell or spigot, with a width greater than 1/10 of an inch, evaluated by an engineer. If there's joints with a vertical or horizontal variation or offset of greater than 3/4 of an inch, make sure that engineer is evaluating it. If there's any joints in the soil and silt tight joints that are allowing a level 3 infiltration, so remember, that's like your runner or your gusher, right? If it's really flowing in there really big, okay, that one, you got to have that evaluated by an engineer. Something's going on there, all right, that we got to look at. All right, and for watertight or leak-resistant joints, okay, again, if the gap is greater than the manufacturer recommendation, it has to be evaluated and looked at by an engineer. If there's any cracks in the joint sealing surface, so your belt or spigot, that are greater than 5/100ths of an inch for a leak resistant, we need to make sure that an engineer is looking at that. Any joints with vertical or horizontal offsets or variations of greater than 3/4 of an inch, you got to have an engineer look at it. And lastly, any joints with any exposed gasket or sealing material, that needs to be evaluated by an engineer. And joints allowing level 2 infiltration on a leak resistant or watertight joint need to be looked at by an engineer, right? We want to make sure if it's got that much water flowing into it, we've got an issue with that joint. We need to make sure an engineer looks at that and makes a recommendation for remediation. All right. So, ASTM C1840 also provides really great requirements for inspection reports criteria for any post-installation inspection program. And this is really important to consider when you're looking at your PII specs or any PII programs that you have. Really, without a clear and concise requirement for a report format for the PII inspection deliverable, the engineer or the owner, you're just going to get a wide range of information and data that you have to sort through and look through and try to interpret on your own. So the guidance that it's given is for each of these pipes, and the NASSCO certification has great guidelines as well. But ASTM C1840 recommends to provide a location and a length and a width of all the cracks to the nearest 5/100ths of an inch for length and to the nearest 100th of an inch for width, if possible. If you're using remote inspection and it's less than 5/100ths of an inch, note less than 5/100ths of an inch, because according to ASTM, C1840, the acceptance criteria, a lot of it is if it's less than 5/100ths of an inch, it's going to be acceptable. So we want to make sure that we're calling that out if it's less than 5/100ths of an inch. Joint separation measurements, if it's in excess of 1 inch, then they recommend that you go to the nearest nearest 10th of an inch. Any other notable observations like debris or any obstructions or anything like that, the recommendation is to provide a still image of each area that exceeds any acceptance criteria, and then reference each of those images back to the inspection video, whether that's at a location in the pipeline, like the distance, the time that it shows up in the video, different things there. So those are some great recommendations that it has in ASTM C1840 for what you should be including in inspection reports. So when I talk to engineers and inspectors, I always like to give them some recommendations to improve their post-installation inspection. And I always encourage them, number one, to adopt a PII program or a post-installation inspection program. And I tell them that because we have this great spec, and I'm obviously a little partial because I help, write it, but use ASTM C1840 as a guide, and then modify it if necessary per project or for your city or your county or the state or whatever it is. Use this as a guide, and then if necessary, go ahead and modify it to meet your needs. I also always recommend that we require NASCO PACP certification for any operators that are performing the video inspections. But I also recommend to engineers and inspectors themselves to consider going through this NASCO PACP certification program as well. I believe that having a robust PII specification and program in place is one of our best defenses against improper installation and can always help municipalities protect their infrastructure investments. So for more information about this topic or any Oldcastle products discussed in the presentation, please email me at jason.allen@oldcastle.com or visit oldcastleinfrastructure.com.